Yeah. So this is
Perfect.
Theo from Intel, where I also work. Theo's actually my boss.
Hey, Bill.
Thank you to Theo for presenting this talk for the original author, which is Bryce, who couldn't make it today. And we'll hear a bit more about hardware design, which is always a fun thing to see in relation to numerics. So, Theo.
Thanks, Bill. So yes, this work is from Bryce Orlowski, who interned with us last year. And essentially, this zooms into a hardware approach to implementing piecewise polynomial approximation to functions. Obviously, we're used to the idea of slicing up a function into regions and approximating using polynomials. If we dived into what that looks like in a hardware setting, essentially the heart of most of this hardware, the things of this type, is a fixed point number where the most significant bits are going into a lookup table, values A, B, and C are coming out. At the same time, there's a square term being computed of the least significant bits, and then we combine it in this sum of product form. So this is very standard. It's very easy to make these things. I've made countless versions of these things over the years. But the question that I posed to Bryce was basically really the limits of the cost of the hardware. What is the smallest lookup table possible, whether that is in the number of rows or the number of columns. This obviously is a quadratic architecture in this case, which is most standard in the hardware that we design, but potentially, depending on the function, there could be many regions that could be linear. This could actually save power. Here we're looking at 2 to the R, where R is the number of bits up here that says how many rows in the lookup table. But there may be cases where we could use the same coefficients for multiple regions. And essentially what I challenged Bryce to provide was, what is the entire design space? And I actually distinctly remember making one of these designs and it violating some accuracy requirement. And my then boss at the time came over and said, well, which row is a problem? And I showed him which row was an issue. And he said, well, what if you change that hexadecimal digit from an F to an E? And hey, presto, it actually worked. Because the issue here is, if we build any of these designs, can we nudge the coefficients in the lookup table? Can we nudge the precisions? So I challenged Bryce to provide the entire design space. So essentially, this is in keeping with an approach to engineering that isn't essentially curve fitting. The standard approach is to pick a curve and force the function into a particular shape, minimax, things of this type. What I challenged Bryce to provide was, can you tell me the entire design space? And then how can we explore within that space? So essentially, what does this problem boil down to? So we're looking at a fixed point input to a function. If you really dive into this, essentially this is trying to fit a curve between integer points. Everything can be rescaled. So essentially the problem we're trying to solve for a particular integer interval for x, does this quadratic fit between these fixed upper and lower bounds, u and l? And all of this can be scaled. So x is an integer in an interval. U and L are the functions, are the upper and lower bounds on what you're allowed to produce. And essentially what we're discussing here is we have buried the acceptable error essentially into these U and L functions. So for the time being, we'll assume that these U and Ls can be computed. And we're assuming that if we wanted 0.6 or things of this type, this can be pre-buried in these U and L functions. So the challenge really is, what is the entire design space? And I will just quickly run through the sketch just to kind of show that these equations were looked into, but apologies in advance, these slides are not meant to be fully parsed. So essentially, what we're trying to look for is all the quadratics curves that fit through a certain interval for a given index, for a given interval I. And so essentially what Bryce did, obviously you start with the simple things. You can rearrange and you can eliminate C. So this is essentially we're about to just do variable elimination on this. And so what that then becomes is a condition for any pairs X and Y in the interval. So anyway, in principle, we're just saying eliminate C. And then of course we can rearrange and eliminate B. This now starts to introduce more variables into the analysis, but essentially what starts to emerge is things that look like derivatives. But of course, these aren't derivatives over the real original function. This is simply for a set of integers X and Y, what is the kind of point-wise derivatives that we would get. And you can eventually rearranging, again, thanks to Bryce for all his excellent work on this, is that once you then eliminate B and rearrange, you can finally get what you would essentially expect, which is down here, you're going to get A over 2 to the K between two rational values. So these D values of W and Z, Y and X, this is just all properties of the underlying U and L. There are no occurrences of A, B, and C in here. So at this point, we are able to basically say we are looking for a fixed point value between two rationals. And so this is, stripping away the variables one at a time. And essentially we do get to a punchline. We'll discuss the cost of what this punchline looks like. Essentially, for the given U and L values and the given interval that X must reside in, we can actually produce necessary and sufficient conditions for the fact that there exists a quadratic that will actually that can actually be used to actually fit this interval. And essentially these capital M's and little m's are types of first derivatives. The condition at the top, of course, is A over 2 to the K will be something around a second derivative. And essentially, these literally are the necessary and sufficient conditions. We can provide pointers to the paper that a quadratic does exist for some values, that A, B, C, and K can exist, such that a quadratic will actually satisfy the constraints. And then once you have the fact that there exists a quadratic, essentially reversing this, this direction, we can actually pull out values for A and K, and then we can rewind and pull out values for B and then C. So I appreciate that was not meant to be parsed in real time, but in principle, you take for the given interval, for the given upper and lower bound functions, you can pick through the algebra. And essentially what Bryce achieved in doing this is what looks like a 4D search are actually two 2D searches. So if you just look at these capital M's and little m's again, these things are not functions of the underlying real valued function. These are literally integer we're computing a rational value for integers X and Y in these cases. So essentially that gave us, does there exist a quadratic? If so, what are the possible values? And so essentially what the tool we built does is it will first compute the minimum possible R. So this is one of the questions I set originally, which is, what is the fewest number of rows in the lookup table that you could ever achieve? And the analysis that we've done about, does there exist a quadratic for a given interval, that allows us to actually calculate the minimal possible R. And then from there, we can then determine the value of K such that feasible A and B exist for a region. And then we basically strip out all of the constraints. So this really is for a given value of R that will actually work. And for each region, we can work out the set of A values that will work. And for each of those values, what are the associated B values, and then in turn C. So we're basically building up the entire design space dictionary. Okay, and then, so that's essentially the value of the work. What's very interesting is having got that full dictionary, we can do some interesting things with it. So actually, let me just, so there's a whole set of questions that we can now answer. We could individually shrink the precisions of A, B, and C. We could merge rows in the lookup table. We could shrink the input to the square function, this x squared term. We essentially have power to explore the design space. And obviously the one I mentioned earlier was we can carefully choose, we can carefully explore what are all the regions that could actually be linear as opposed to quadratic. So what do the results look like? So I think the real value add is we were able to determine the design space. So what is the computational cost of this? So what we did to at least kick the tires on the approach is we didn't parallelize this at all. The search, those 2D searches are easily parallelizable. In the worst case, we can achieve single precision within 1 to 3 days of some functions. And obviously, if we did parallelize this, then we could achieve speed up in this area. So this full-blown design space creation is not infeasible. We're discussing hardware design, where intricately picking through a design and constructing the best hardware can easily take weeks. Have we done something novel? Is there anything really of interest here? We found cases where we were able to answer the question, have we built something new that didn't exist before? So as an example, for a B-float reciprocal, we did work out that you could use only 2 regions instead of 4. So we are producing different results compared to things such as Flopico. Were we able to build anything competitive out of this? And essentially, these are area delay curves for different hardware. And what's quite interesting about this is for a half precision reciprocal. So we can see that a standard ASIC competitor being Synopsys Designware is in the middle of this. And these other curves you're looking at are for how many lookup bits were in the table. So we are able to produce hardware that is better, but the real punchline is we generated confusion. And the real confusion is we have this enormous design space, but we really don't know what to do with it yet, to be honest. And so one of the interesting things is the R value, which is the number of bits that go into the lookup table. Essentially, what is the best setting for that? Do you really want the smallest R value? And what you're looking at here is particular points where DW is designware, which is the competition. And then these points in the area delay space are the different R values. So you can see here that as the R value grows, there is some sweet spots that occur. It's not obvious, and it will be very function dependent. So these red dots are actually a 16-bit log2. The blue ones are for a 10-bit log2. And so there is this question, how do you actually explore this design space? So essentially, the value of the work was essentially give me the entire design space. And this is feasible for up to a 32-bit thing. We haven't even touched the parallelism of this. And we can, it can be used to find smaller lookup table sizes, shrinking versus various hardware aspects. But the thing we don't know yet is what to do with this enormous power. So we can play all these interesting hardware games. We haven't yet fully worked out how to explore this clearly very large design space, because we have the full dictionary. How do we actually choose to navigate it?
Awesome. Thank you, Theo. I think we're about to head into the next planned break period, but we can go ahead, and if anyone has any questions, present them or ask here. I see Peter has something.
Yeah, so do you think it's easier for this kind of problem to find the Pareto frontier than to generate the whole design space? Does that seem feasible?
Oh, yes. I think I think the intricacy is, if we go back to this list, I think the strange aspect of this is once we have the dictionary, we can think about the ways in which we can order the optimizations. And this is when it gets interesting. So I could, as I just kind of had some results, is smaller R better? So I can vary R. But the weird thing is, even if I fix R, I could look at this and say, well, should I then tackle the bit width of A first? How does that impact this? So I have all these things I could do, and I could indeed pick a decision procedure around how I'm going to design this. And it's really not, what's really interesting about this hardware is some of these decisions, are they essentially affecting the speed or the area or a bit of both? But yes, we could pick variables, optimization ideas, and produce Pareto surfaces or walk across it. But what's very interesting is we have all these beautifully interconnected hardware consequences. So how do we order these things? That kind of a factorial ordering of optimizations we could do. But yes, we can walk along a Pareto surface if we can work out which Pareto surface to walk along.
And one of the big challenges here is that the true Pareto surface that you want is going to be like the, that area delay curve that you see for, so it's like it would be like something for that. And the one of the bottlenecks here is just going to be that every single point you want to explore on that true surface is going to be like another, 15 minutes at least to run logic synthesis on it. So it becomes very expensive without having some sort of intermediate hardware cost proxy or something like that. So yes, it's funny that you mentioned that, though. We're definitely a community of Pareto surface lovers here. So so Mohit has the hand raised here. I think that's not the clapping emote.
Yeah. Hi. This is like a really great presentation. So regarding the illustration that you showed where you had lookup tables and the other stuff, I guess my question is, how do you define the lookup table? Is it the number of significant digits that like in the representation, or like how do you define lookup table? And that's my question.
Oh, okay. So yes, if we go back to the original equations, let's go. Oh, there we go. So where do these lookup table values come from? So let's say we know that a particular R value will work. Then for a particular region, we actually are able to calculate that A over 2 to the K resides between two rational values. So actually, we know what we can then obviously infer what is the smallest K that would actually work. And then once we fix a particular K value, we don't have to use the minimum one. This will give us a range of integers A of that precision that will then work. And then if you actually plug it back into the previous, we then end up with an integer range of B. And again, for each of the rows, the integer value of B could be such that we could find what is the minimal precision of B that could ever work across the entire, for all the regions. And then in turn, for C will be another range of integers. So essentially how the lookup table is formed is once you have a precision of A, B, and C that could work, you're going to have a range of values that you can choose from. It's essentially an integer dictionary that then you use to populate the lookup table.
Okay, cool, thanks.
All right, I think we'll transition to the break, although everyone is welcome to hang around and continue any sort of discussion or ask additional questions. And I think we will resume. So I will pause the recording one moment.